Hello and welcome to another GCSE revision video, and in this video we're going to be continuing on from the previous video about standard form. In this video we're going to be looking at why do we bother with standard form in the first place, and then we're going to do some calculations using standard form. Now, in the real world we would usually only use standard form to describe really big or really small numbers, those which would be very difficult or impossible to write down otherwise. And at the end of the video, we're going to have a go at trying to estimate the age of the universe itself. When we're adding or subtracting numbers in standard form, the first thing to do is make the index the same, and then we can add or subtract the coefficients. Let's take, for example, 4.0 times 10 to the power negative 3, and we're adding 2.5 times 10 to the power negative 2. Well, to do that, the first thing we need to do is make sure the indices are the same. So 4.0 times 10 to the power negative 3 can be converted to 0.4 times 10 to the power negative 2, simply by moving the decimal point one place to the left and adding 1 to the index. Now that the indices are the same, we can just add the coefficient. So 2.5 plus 0.4 is 2.9. So 4.0 times 10 to the power negative 3 plus 2.5 times 10 to the negative 2 is 2.9 times 10 to the power negative 2. Okay, so what about multiplying numbers in standard form? Well, we've got, for example, 2 times 10 to the power 3 multiplied by 2 times 10 to the power negative 2. In this case, since we're multiplying all the way throughout, all we do is multiply the coefficients and then add the indices like we did with the law of indices. So 2 times 2 is 4. 10 to the power 3 times 10 to the power 2 is equal to 10 to the power 3 minus 2, which is 10 to the power 1. So 2 times 10 to the power 3 times 2 times 10 to the power negative 2 is just 4 times 10 to the power 1. So when we're adding or subtracting, we make the indices the same, then we can add or subtract the coefficients. When we're multiplying or dividing, we just multiply or divide the coefficients and then treat the indices like we did with the law of indices. Okay, and that brings us to the somewhat cosmic conclusion to our video. And I'm going to leave you with the question, how old is the universe? If we're given that the universe is expanding at a rate of 70 kilometers per second per megaparsec, that figure, by the way, is commonly known as the Hubble constant. If we know that 1 megaparsec is 3 times 10 to the power 6, or 3 million light years, and 1 light year is 1 times 10 to the power 13 kilometers, that's 10 trillion kilometers. If we convert 1 megaparsec to kilometers, then the kilometers will cancel out of the Hubble constant, just leaving us with reciprocal seconds. And if we take the reciprocal of those reciprocal seconds, that will give us an estimation of the age of the universe known as Hubble time. You will now be fully empowered to estimate the age of the universe for yourself. Okay, I'll leave that one with you to think about. If you can pause the video, have a think about it yourself, and then I'll give you the answer at the end. Okay, so how did you get on with that? Let's have a look at our answer. We're told that the Hubble constant is 70 kilometers per second per megaparsec. Okay, first of all, let's just explain what that means. That means that two galaxies that are 1 megaparsec apart will be moving away from each other at a rate of 70 kilometers per second. If they were 2 megaparsecs apart, they'd be moving away from each other at 2 times 70, or 140 kilometers per second. If they were 3 megaparsecs apart, they'd be moving away at 3 times 70, or 210 kilometers per second, and so on. And we want to know how long ago were all these galaxies on top of each other. So what we're doing now is converting megaparsecs to kilometers. So 1 light year is equal to 1 times 10 to the power 13 kilometers, and 1 megaparsec is equal to 3 times 10 to the power 6 light years. So that's basically saying that there are 3 million light years in a megaparsec and 10 trillion kilometers in a light year. So that means there are 10 trillion times 3 million kilometers in a megaparsec. This is why we use standard form, so that we can make the calculations easy. Imagine trying to deal with all those noughts. Okay, so that's equal to, well, the coefficients are just 1 times 3, and that's times 10 to the power, and the law of indices says 10 to the power 13 times 10 to the power 6 is equal to 10 to the power 13 plus 6. So that's equal to 3 times 10 to the power 19 kilometers, which is 1 megaparsec. So if we divide the Hubble constant then, so the Hubble constant is basically saying that galaxies are receding at a rate of 70 kilometers per second for every 3 times 10 to the power 19 kilometers. Well, the units cancel, leaving us reciprocal seconds. So now 70 divided by 3 times 10 to the power 19, well, we can cancel that 0 and turn that into an 18. So that's equal to 7 over 3 times 10 to the power 18. And that's reciprocal seconds. Okay, so that's equal to, well, that's 7 over 3 times 10 to the power 1 over 10 to the power 18, or 10 to the power negative 18 reciprocal seconds. Now, if we want to get that into actual seconds, we're going to need to take the reciprocal of the whole thing. So if we take the reciprocal, and the reason I'm doing it this way rather than an easier way is because I'm trying to use these as many calculations as I can involving standard form, so that you get used to using standard form in calculations. So that's 1 over 7 over 3 times 10 to the power negative 18 reciprocal seconds. So that's equal to 1 over 7 over 3, which gives us some practice with our fractions, multiplied by 1 over 10 to the power negative 18, multiplied by 1 over reciprocal seconds. So that's equal to, well, 1 over 7 over 3 is just 3 over 7. You just invert the denominator, and there's a video on dividing fractions if you want. And then we multiply by 1 over 10 to the power negative 18. Well, we know that 1 over 10 to the power negative 18 is just 10 to the power 18, because 10 to the power negative 18 means 1 over 10 to the power 18. So 1 over 10 to the, 1 over 10 to the power 18 is just 10 to the power 18. So then that's multiplied by, and then our units are 1 over reciprocal seconds, which are just seconds. In fact, we don't need that multiplication sign. And there you have it, Hubble time. I'm going to call it TH0 for Hubble. H0 is the Hubble constant, so TH0 is just Hubble time. So the age of the universe is 3 over 7 times 10 to the power 18 seconds. Okay, that's not very fulfilling. Let's get our calculator out and see how much that is in years. So we'd pull out our calculator. So we do 3 divided by 7. And now we're multiplying by 10 raised to the power of 18. So that's the number written out in full. And that's how many seconds. So if we divide by 60 seconds in a minute, that's how old the universe is in minutes. And we divide by 60 minutes in an hour, and that's how old the universe is in hours. And then we divide by 24 hours in a day, and that's how old the universe is in days. And then we divide by 365.25 days in an average Gregorian year, or in a year. Okay, so that's 13,580,609,063. So that's our thousands. That's then our millions, and that's then our billions. So that's about 13.6 billion years. Okay, now for honesty's sake, we're only allowed to round up to one significant figure. So that's about 10 billion years. It is just a coincidence that our calculations come out to very, very close to what scientists actually say is the real age of the universe. And it's quite nice and tempting to say, oh, look, 13.5, 13.6 billion years, that's very, very close to what astronomers say is the age of the universe. Our calculations, we can only really be sure to the nearest one significant figure, so that's 10 billion years. The reason scientists can be more accurate is because they do much more accurate calculations with much more accurate figures, and they do a lot more advanced maths. But it is really cool that we got 13.5 billion and they get 13.5 billion, which is really nice considering we're only using GCSE level maths. Okay, I hope that was interesting at least, and I'd like to wish you all the best with your revision and all the best with your exams, and I'll see you in another video.